When we first learn about the physical world, we are taught a simple and reassuring idea: solid objects stop things. A wall blocks sound, blocks people, blocks light, and separates one space from another. This idea works well at the human scale, where experience is shaped by everyday interactions. But when we look closely at nature, especially at the level of atoms and subatomic particles, this comforting simplicity begins to break apart. The strange difference between matter particles and light in interacting with walls is one of the clearest examples of how deeply our intuition fails when confronted with the true rules of reality. To understand this difference, we must first understand what a wall actually is. A wall feels solid to us because the atoms in our body strongly repel the atoms in the wall. This repulsion is not due to physical contact in the way two stones collide, but due to electromagnetic forces between electrons in atoms. Atoms themselves are mostly empty space. If you could magnify matter to an extreme degree, you would see tiny nuclei surrounded by vast regions of emptiness, held together by invisible fields. Solidity is not a property of matter being packed tightly together. It is a property of forces resisting overlap. Light enters this story as a special form of energy. It is an electromagnetic wave, a vibration of electric and magnetic fields moving through space at a fixed speed. When light reaches a wall, it encounters billions upon billions of charged particles, primarily electrons, inside the atoms of the wall. These electrons are extremely responsive to electromagnetic fields. As soon as light touches the surface, the electrons begin to move, oscillate, and absorb the incoming energy. The light is either reflected, scattered, or converted into heat. This interaction is so efficient that for many materials, light simply cannot pass through. The wall becomes opaque, not because it is thick in a mechanical sense, but because it is electrically active. Matter particles behave differently because they are not all governed by the same type of interaction. Some particles carry electric charge, like electrons and protons, while others do not, or interact only weakly with electric fields. This difference alone creates a dramatic contrast in how they experience a wall. A particle that barely interacts with the electromagnetic forces inside the wall can pass through almost as if the wall were not there at all. In this sense, the wall's effectiveness depends less on its physical presence and more on the kind of interaction taking place. Even when particles do interact with the wall, they do so in ways that defy classical logic. Unlike light, which is always a wave, matter particles exist in a strange dual state. They behave like particles when measured, but like waves when traveling. This wave, like nature, allows matter to spread out, to exist as a probability distribution rather than a single point. When such a wave encounters a wall, it does not simply stop at the surface. Instead, part of the wave extends into the barrier itself. The wall is no longer an absolute boundary, but a region where the particle's probability gradually decreases. This is where the intuitive idea of blocking breaks down completely. In classical physics, a barrier is a strict dividing line. Either something has enough energy to cross it, or it does not. But in quantum physics, barriers are negotiable. If the particle's wave extends far enough into the wall, there is a chance that it will appear on the other side. This chance may be extremely small, but it is real. The wall has not been broken or penetrated in a mechanical sense. Instead, the particle has exploited the wave nature of reality itself. Light, in most everyday situations, does not enjoy this freedom. Because it couples so strongly to the electrons in matter, its wave is quickly disrupted. The wall absorbs the wave before it can meaningfully extend beyond the surface. The probability of light appearing on the other side of an opaque wall is effectively zero under normal conditions. This difference does not mean light is weaker or less fundamental. It means its mode of existence is tied tightly to electromagnetic interaction, which walls are designed by nature to resist. Another key difference lies in how information and energy are transferred. Light carries energy in discrete packets called photons, and these photons are easily absorbed by atoms. When a photon strikes an electron, it can transfer its energy completely, vanishing in the process. Many matter particles, on the other hand, require very specific conditions to interact. If those conditions are not met, the particle simply continues on its path. The wall does not get a chance to stop it. This contrast becomes especially striking when considering particles like neutrinos. Neutrinos are produced in enormous numbers by the Sun, nuclear reactions, and cosmic events. They pass through Earth, through walls, through entire planets, almost without interacting at all. For a neutrino, a wall is little more than empty space. Light, which cannot pass through the same wall, seems fragile by comparison. Yet light is stopped not because it is weak, but because it is too interactive. It cannot ignore matter the way neutrinos do. What this reveals is that walls do not have a universal meaning in physics. A wall is not an absolute object that blocks everything equally. It is a selective filter that depends on the type of entity encountering it. To light, a wall is a storm of electric forces. To some particles, it is a faint whisper. To others, it is a probabilistic challenge rather than a firm boundary. This realization forces us to reconsider what we mean by separation and containment. The everyday world is shaped by dominant interactions, especially electromagnetism. That is why light, sound, and physical objects obey familiar rules. But beneath these rules lies a deeper layer of reality where interactions vary in strength, where waves replace solid points, and where barriers lose their finality. The strange difference between matter particles and light in interacting with walls is not a small technical detail of physics. It is a window into the structure of the universe. It shows that what feels solid is emergent, not fundamental. It shows that stopping something is not about size or strength alone, but about how deeply two things are allowed to interact. Most importantly, it reminds us that nature does not care about human intuition. It follows its own logic, one in which walls can be both solid and permeable at the same time, depending entirely on who or what is trying to pass through. When we extend this idea further, the difference between matter particles and light interacting with walls begins to reveal a deeper lesson about how reality organizes itself. A wall is not a single object with a single behavior. It is a complex system made of atoms, fields, and forces, all operating according to quantum rules. What happens at the surface of a wall depends entirely on what arrives there, and how that arriving entity is allowed to interact with those rules. Light as an electromagnetic phenomenon is inseparable from electric charge. Every photon is a ripple in electromagnetic fields, and those fields immediately influence charged particles. In a solid wall, electrons are bound within atoms, but they are not frozen. They respond instantly to electromagnetic disturbances. When light reaches the wall, the electrons begin to oscillate in response to the incoming wave. This oscillation drains energy from the light, converting it into heat or re-emitting it in different directions. The process happens so quickly and so thoroughly that light rarely progresses beyond the surface. In effect, the wall neutralizes light by engaging with it completely. Matter particles do not always trigger this response. Some particles carry no electric charge at all, and others interact only under very specific circumstances. For these particles, the wall's electrons are not effective gatekeepers. The wall lacks the handles needed to grab onto them. As a result, these particles move through the atomic lattice with minimal disturbance, slipping through gaps that are not physical holes but regions where interaction simply does not occur. Even for charged particles like electrons, the interaction is not always absolute. At small scales, energy and position cannot be pinned down perfectly. This uncertainty is not due to experimental flaws, it is built into nature itself. A particle approaching a wall does not have a sharply defined boundary where it must either pass or stop. Instead, there is a region where outcomes blur. The particle's wave spreads into the barrier, and the wall becomes a zone of diminishing probability rather than a rigid line. This probabilistic behavior creates a subtle but powerful distinction between light and matter. Light tends to behave collectively when interacting with matter. Enormous numbers of electrons respond together, creating a strong, unified resistance. Matter particles, especially single particles, encounter the wall individually. Their interactions are local, discrete, and sometimes incomplete. This difference in scale and coordination gives walls their apparent authority over light while leaving loopholes for particles. Another factor lies in how momentum and energy are exchanged. When light hits a wall, momentum is transferred efficiently. The wall can absorb or reflect the photon without violating conservation laws because the entire structure of the wall participates in the interaction. For certain particles, especially those with very small masses or weak interactions, transferring momentum is much harder. The wall cannot easily absorb their presence, so the interaction often fails to occur at all. This is why walls feel solid to us but remain porous to the universe at large. Human senses evolved to detect electromagnetic interactions. Our vision, touch, and hearing are all mediated by electromagnetism. We perceive the world through the same interaction that stops light. As a result, we mistake this interaction for an absolute feature of reality. In truth, it is just one dominant force among several, and not all entities are subject to it in the same way. What appears as a contradiction, particles passing through walls while light cannot, is actually a demonstration of consistency. Nature applies the same rules everywhere, but those rules produce different outcomes depending on context. A wall stops what it can interact with, it fails to stop what it cannot. There is no special exemption, no trick, no violation, only differences in coupling, probability, and scale. This understanding reshapes how we think about boundaries. In classical thinking, boundaries are rigid and universal. In quantum reality, boundaries are conditional. They depend on energy, interaction strength, and the nature of the entities involved. A wall is a strong boundary for light, a weak boundary for some particles, and a probabilistic boundary for others. The universe, then, is not divided into sealed compartments. It is layered, interconnected, and subtly permeable. Even the most solid objects are transparent to certain forms of existence. This does not make walls meaningless, but it makes them relative. Their power lies not in their material thickness, but in the interactions they enable. By understanding why particles can pass through walls while light cannot, we uncover a more general truth. Reality is not governed by what seems solid, but by what can interact. The deepest structures of the universe are not built from barriers, but from relationships between forces, fields, and probabilities. What stops one thing may be invisible to another, and what appears impossible at one scale becomes inevitable at another. In this way, the wall ceases to be an obstacle and becomes a lesson, revealing that the universe is far more flexible, subtle, and surprising than our everyday experience ever suggests. At the heart of the mystery of particles passing through walls lies a concept that fundamentally reshaped our understanding of nature, the wave-particle nature of reality. This idea challenges the deepest assumptions we make about what things are and how they move. For centuries, physics was built on a simple division. Particles were thought of as tiny solid objects with definite positions, while waves were seen as spread-out disturbances that flowed through space. Light was classified as a wave, and matter was classified as particles. This neat separation made the world understandable and predictable. But the universe did not obey this division, and when experiments began to probe the microscopic scale, reality revealed a far more unsettling truth. The first cracks appeared when light itself began behaving like a particle. Experiments showed that light could knock electrons out of metal surfaces only if it arrived in discrete packets of energy. These packets, later called photons, acted like particles delivering energy in sudden, localized impacts. At the same time, light continued to show unmistakable wave behavior, such as interference and diffraction. Light was not one thing or the other. It was both, depending on how it was observed. Soon after, matter began to betray its own secrets. Electrons, long assumed to be tiny charged particles orbiting atomic nuclei like planets around a star, were found to produce interference patterns when passed through narrow openings. These patterns were identical to those produced by waves in water or light passing through slits. Even when electrons were fired one at a time, the wave-like pattern slowly emerged as if each electron interfered with itself. This result was deeply disturbing. A single particle, traveling alone, behaved as though it were spread out across space. This wave-particle duality is not a flaw in measurement or a trick of instruments. It is a fundamental feature of reality. At the quantum level, objects do not possess definite properties until they are measured. Instead, they are described by wave functions, mathematical entities that encode probabilities rather than certainties. A particle does not travel along a single path, it explores many possible paths at once, existing as a superposition of possibilities. When such a wave-like particle approaches a wall, the classical picture fails completely. In classical terms, a particle either hits the wall and stops or bounces back. But a wave does something different. It spreads, bends, and partially penetrates obstacles. This spreading is not a metaphor. It is a real physical description of how quantum objects behave. The particle's presence is not confined to a single point, but distributed across space, including regions that classical intuition would forbid. This is where the wall loses its absolute authority. The wall is no longer a hard surface confronting a solid object. It is an interaction region where waves meet waves. The particle's wave interacts with the electromagnetic and nuclear fields inside the wall. In some regions, the wave is suppressed, in others it survives. The outcome is not predetermined but probabilistic. There is a chance that the wave extends beyond the wall, and with it, the possibility that the particle will be detected on the other side. Light, despite being a wave, behaves differently because of the type of wave it is. An electromagnetic wave interacts strongly with charged particles. When light reaches a wall, its wave is rapidly absorbed or reflected by the collective response of electrons. The wave collapses almost immediately, leaving little room for ambiguity. Matter waves, by contrast, do not always provoke such a unified response. Their interaction depends on mass, charge, energy, and the specific structure of the barrier. The wave-particle nature of matter also explains why size alone is not the deciding factor. It is tempting to think particles pass through walls because they are smaller than atoms. But this is misleading. Size is not the key variable in quantum mechanics. Wavelength is. The wavelength associated with a particle depends on its momentum. Slower particles have longer wavelengths, meaning their wave nature becomes more pronounced. A longer wavelength allows the particle's wave to interact with barriers in a more diffuse and subtle way, increasing the chance of non-classical behavior. This dual nature forces us to abandon the idea of particles as miniature billiard balls. A better, though still imperfect, picture is to imagine particles as events that spread influence rather than objects that occupy space. They are defined not by where they are, but by where they could be. The wall, in this framework, is not a fixed obstacle but a filter that reshapes possibilities. Another unsettling consequence of wave-particle duality is that observation itself plays a role in determining outcomes. When a particle is not observed, its wave evolves freely, exploring all allowed possibilities. When a measurement occurs, the wave collapses into a definite outcome. This collapse is not something we fully understand, but its effects are undeniable. The act of detection turns a wave of possibilities into a single event. In the case of a particle passing through a wall, detection on the far side confirms that one of those improbable possibilities has become real. Light behaves differently in this regard, because its interaction with matter often forces an immediate collapse. The moment light touches the wall, it is measured by countless electrons responding to its presence. There is no prolonged exploration of possibilities. The outcome is fixed almost instantly. Matter particles, especially those interacting weakly, may travel long distances without being measured at all, allowing their wave nature to dominate. The wave-particle nature of reality also explains why this behavior is invisible at human scales. Large objects have extremely tiny wavelengths due to their large mass and momentum. Their wave nature is effectively compressed into a region so small that it becomes unobservable. As a result, everyday objects behave classically. Walls feel solid, boundaries feel absolute, and the quantum flexibility of matter is hidden from view. It is not absent, it is simply overwhelmed by scale. What emerges from this understanding is a universe that is fundamentally non-binary. Objects are not either waves or particles. They are quantum entities whose behavior depends on context. Walls are not simply barriers. They are environments that shape probability. Light and matter differ not because one is privileged over the other, but because they participate in different kinds of wave behavior and interaction strengths. The wave-particle nature of reality dissolves the apparent paradox of particles passing through walls while light cannot. It reveals that the difference lies not in defiance of physical law, but in obedience to deeper laws that govern how possibilities evolve. At the quantum level, reality is not built from solid objects colliding in empty space. It is built from overlapping waves of probability, interacting fields, and moments of collapse that bring one outcome into being. In this deeper view, a wall is no longer an absolute divider. It is a region where the universe negotiates outcomes. Sometimes the negotiation ends in rejection, sometimes in reflection, and sometimes, quietly and unexpectedly, in passage. When we continue deeper into the wave-particle nature of reality, an even more radical picture emerges, one that challenges not just how particles move, but what it means for something to exist at all. In the quantum world, existence is not a fixed state but a range of possibilities. A particle is not fully there in one place until an interaction forces it to be. Until that moment, it exists as a spread-out influence, described not by certainty but by likelihood. This is the key reason walls lose their absolute power at small scales. A wall, from a quantum perspective, is not a smooth, continuous surface. It is a dynamic system of atoms vibrating, electrons shifting, and fields fluctuating. These microscopic motions never stop, even at very low temperatures. When a matter wave approaches such a system, it does not encounter a single obstacle, but a constantly changing landscape. The particle's wave adjusts itself to this landscape, splitting into components that reflect, decay, or continue forward. Each possible outcome exists simultaneously within the wave function. This simultaneous existence of multiple outcomes is one of the most difficult ideas to accept, yet it is central to quantum behavior. The particle does not decide in advance whether it will pass through the wall or not. Both possibilities are present. The universe allows these possibilities to evolve together until an interaction forces a resolution. When a particle is eventually detected, the wave collapses into one outcome and the other possibilities vanish. The wall, in this sense, is not a judge that forbids passage but a participant in a probabilistic process. Light rarely enjoys this freedom because its wave is constantly interacting. The electromagnetic nature of light makes it highly visible to matter. Every charged particle in the wall becomes a detector. This continuous detection prevents the photon's wave from spreading far into the barrier. The wave is interrupted again and again, collapsing almost immediately. Matter waves, especially those of weakly interacting particles, can travel long distances without interruption, preserving their quantum flexibility. This difference highlights an important truth. Wave-particle duality is not symmetrical in practice. While all quantum entities share this dual nature, the environment determines which aspect dominates. For light in a solid wall, the particle-like interaction dominates. For some matter particles, the wave-like behavior dominates. The environment selects the behavior, not the entity itself. Another crucial element is coherence. A quantum wave maintains coherence when its different parts remain linked, able to interfere with one another. Coherence allows a particle to behave as a unified wave. Walls tend to destroy coherence for light because of the overwhelming number of interactions. Matter particles, under the right conditions, can maintain coherence even while passing near or through material barriers. When coherence survives, the wave remains capable of producing non-classical outcomes. This explains why quantum effects are fragile yet powerful. They require isolation from excessive interaction. A wall, paradoxically, can sometimes provide that isolation by failing to interact strongly. In such cases, the wall does not collapse the wave but allows it to evolve. What appears solid becomes transparent, not physically, but quantum mechanically. The wave-particle nature of reality also reshapes our understanding of causality. In classical physics, causes lead directly to effects. A particle hits a wall, therefore it stops. In quantum physics, causes influence probabilities rather than outcomes. The wall influences how likely different futures are, but it does not dictate a single future. This subtle shift changes everything. The universe no longer runs like a machine with fixed outcomes, but like a system that explores possibilities within strict mathematical rules. This exploration does not mean randomness without order. Quantum probabilities are precise and predictable in aggregate. While the fate of a single particle is uncertain, the behavior of many particles follows exact patterns. Walls block light reliably because the probabilities overwhelmingly favor absorption or reflection. Particles occasionally pass through because the probabilities, while small, are not zero. Reality balances uncertainty with consistency. At larger scales, this balance produces the illusion of certainty. The wave-particle nature of macroscopic objects becomes invisible because the probabilities of non-classical behavior shrink to nothing. A human-sized object tunneling through a wall is not forbidden in principle, but the probability is so unimaginably small that it effectively never happens within the lifetime of the universe. The rules are the same, the scale is different. This continuity between the microscopic and macroscopic worlds is one of the most profound implications of wave-particle duality. There are not two sets of laws, one for the small and one for the large. There is one set of laws applied across scales, producing different experiences. Walls feel absolute because the probabilities align that way, not because the universe enforces a hard boundary. Understanding this dissolves the sense of mystery without diminishing the wonder. Particles do not cheat or slip through walls by breaking rules. They follow the rules perfectly, rules that allow waves of possibility to exist, spread, and sometimes succeed against intuition. Light obeys the same framework, but its interactions anchor it firmly to matter, limiting its freedom. In this light, the wave-particle nature of reality is not merely a technical detail of physics. It is a statement about how existence itself is structured. Reality is not built from objects alone, but from relationships, interactions, and probabilities. What something is cannot be separated from how it interacts and how it is observed. The wall, once thought to be a symbol of certainty and separation, becomes a reminder of this deeper truth. It shows that boundaries are not absolute features of the universe, but emergent results of interaction. To some entities, the wall is an insurmountable barrier. To others, it is a statistical challenge. To the universe as a whole, it is simply one configuration among many, shaping but not dictating what can happen. In embracing the wave-particle nature of reality, we learn that the universe is not rigid but responsive, not binary but nuanced. It allows passage where intuition expects resistance and enforces limits where freedom seems possible. This hidden flexibility is not a flaw in nature but its defining strength, revealing a cosmos that is subtle, consistent, and far more imaginative than any classical picture ever allowed. Quantum tunneling is one of the most counterintuitive and revealing phenomena in all of physics, and it lies at the core of understanding how particles can pass through walls that light cannot. To grasp its meaning, we must first abandon the idea that barriers are absolute. In the everyday world, a barrier is final. If you throw a ball at a wall and it does not have enough energy to break through, it stops. There is no ambiguity, no probability, no exception. Classical physics is built on this certainty. Quantum physics is not. At the quantum scale, energy, position, and motion are governed by rules that do not allow such clean outcomes. A particle approaching a wall is not a tiny object traveling along a single path. It is a quantum entity described by a wave function. a mathematical expression that represents a spread of possible positions and energies. This wave function does not abruptly end at the surface of a barrier. Instead, it gradually decays inside it. The wall becomes a region where the particle's presence fades rather than disappears. This fading is the key to tunneling. Even if a particle does not have enough energy to climb over a barrier in the classical sense, its wave function still penetrates into the barrier. As long as the wave does not drop to exactly zero, there remains a non-zero probability that the particle will emerge on the other side. This probability may be extremely small, but quantum mechanics does not allow it to be dismissed. If something is not forbidden, it can happen. The idea that a particle can appear on the far side of a wall without ever possessing the energy to cross it feels like a violation of logic. But nothing is being violated. Energy is conserved. No laws are broken. What changes is the way those laws operate. In quantum mechanics, energy conservation applies globally, not locally in the way classical intuition demands. The particle does not borrow energy or sneak through a crack. It exists in a state where crossing the barrier is simply one of the allowed outcomes. The thickness and strength of the wall still matter. A thicker barrier causes the wave function to decay more rapidly, reducing the probability of tunneling. A higher barrier makes the decay steeper still. This is why tunneling is rare for macroscopic objects and common only at microscopic scales. The wave nature of large objects is so compressed that their probability of tunneling through everyday barriers is unimaginably small. In practice, it never happens. But at the level of electrons and other subatomic particles, tunneling becomes a routine feature of reality. This phenomenon directly explains how particles can pass through walls while light usually cannot. Light interacts with matter in a way that causes its wave to be absorbed or reflected almost immediately. The electromagnetic barrier presented by a wall is extremely effective at suppressing light's wave function. For many particles, however, especially those with appropriate energies and wavelengths, the barrier does not completely extinguish the wave. The wall becomes semi-transparent in a probabilistic sense. Quantum tunneling is not a rare curiosity confined to laboratories. It is essential to the universe as we know it. The fusion reactions that power the sun depend on tunneling. Protons in the sun's core do not have enough energy to overcome their mutual electrical repulsion in classical terms. If classical physics were the whole story, the sun would never ignite. Tunneling allows protons to get close enough for nuclear forces to take over, releasing the energy that sustains stars and life itself. On Earth, tunneling underlies modern technology. Semiconductor devices rely on tunneling to control the flow of electrons at small scales. The scanning tunneling microscope, one of the most powerful tools in science, uses tunneling to image individual atoms. An electron tunnels across a tiny gap between a probe and a surface, producing a measurable current. This would be impossible under classical rules, yet it works with astonishing reliability. What makes tunneling especially profound is that it turns barriers into negotiable regions rather than rigid boundaries. A wall does not say no in an absolute sense. It says unlikely. The universe, at its core, is not deterministic in the classical way. It operates on probabilities. Most of the time, those probabilities line up with our expectations. Sometimes, at small scales, they do not. Light does not typically enjoy this loophole because its interaction with matter forces an immediate outcome. The wave function of light collapses almost as soon as it encounters a wall. The electrons in the wall measure the photon by absorbing or reflecting it, leaving no extended wave to explore the barrier. Matter particles, especially when isolated and weakly interacting, can remain unmeasured long enough for tunneling to occur. This difference highlights a deeper truth about nature. Barriers are not defined solely by material strength, but by the interactions they enable. A wall is powerful against electromagnetic waves because it is built from charged particles. It is less powerful against entities that do not engage strongly with those charges. Quantum tunneling is the mathematical expression of this selective weakness. As we push deeper into the quantum world, the notion of inside and outside begins to blur. A particle is not strictly on one side of a wall or the other until it is observed. Until then, it exists in a superposition that spans regions we would normally consider forbidden. Tunneling is not the particle cheating the rules, it is the particle obeying rules that are far more subtle than everyday experience suggests. In this way, quantum tunneling reveals that walls are not fundamental features of reality. They are emergent structures that arise from dominant interactions at certain scales. Beneath those interactions lies a universe where probability replaces certainty, and where even the most solid obstacles can, under the right conditions, be quietly crossed. Quantum tunneling completes the picture by revealing that barriers are not the final authority we once believed them to be. In classical thinking, a barrier is absolute. If an object lacks the energy to cross it, motion stops and the story ends. This logic feels undeniable because it works perfectly in daily life. A ball thrown at a wall either breaks through or bounces back. There is no third option. Yet at the quantum scale, nature quietly allows a third outcome, one that does not violate energy conservation, but instead redefines what a barrier truly means. A quantum barrier is not a solid cliff with a sharp edge. It is a region where conditions change, where energy landscapes rise and fall. When a particle approaches such a region, it does not encounter a simple stop sign. Instead, its wave function begins to respond to the new conditions. Inside the barrier, the wave does not vanish instantly. It decays gradually, fading rather than ending. This fading is crucial. As long as the wave exists, even faintly, there remains a chance of continuation beyond the barrier. This behavior has no classical equivalent. Classical objects cannot partially exist inside forbidden regions. Quantum objects can. They borrow no energy, break no rules, and yet appear on the other side. The probability may be tiny, but it is never exactly zero. The universe, at its deepest level, refuses to enforce absolute prohibitions. What makes this so profound is that tunneling is not rare or exotic. It is happening constantly, everywhere. Inside the sun, nuclear fusion relies on tunneling. Protons should repel each other strongly due to their positive charges. Classically, they would never come close enough to fuse. Yet tunneling allows them to cross the energy barrier created by electromagnetic repulsion, releasing the energy that powers stars. Without tunneling, stars would not shine and life would not exist. On Earth, tunneling enables technologies that shape modern civilization. In electronic components, electrons tunnel through insulating layers that should be impenetrable. In scanning tunneling microscopes, scientists use tunneling currents to map surfaces atom by atom, revealing structures smaller than any optical microscope could resolve. These devices do not exploit a loophole in physics, they exploit the core behavior of reality itself. Light, however, rarely benefits from tunneling in ordinary materials. Its interaction with matter is so strong that its wave function is rapidly extinguished. The barrier does not merely suppress the wave, it absorbs it. For tunneling to occur, the wave must survive inside the barrier long enough to re-emerge. For light hitting an opaque wall, this survival time is effectively zero. The wall does not allow the wave to decay gently, it destroys it through interaction. This difference highlights an essential truth. Tunneling depends not only on energy, but on interaction strength. A weakly interacting particle can maintain its wave inside a barrier, giving tunneling a chance. A strongly interacting wave collapses too quickly. The barrier's power lies not in thickness alone, but in how aggressively it couples to the incoming entity. As we push deeper into this idea, tunneling begins to feel less like a trick and more like a natural consequence of continuity. In quantum mechanics, wave functions must be continuous. They cannot abruptly drop to zero without reason. This continuity enforces the presence of the wave inside barriers. The universe prefers smooth transitions over sharp discontinuities, even when those transitions violate our classical expectations. This smoothness also explains why tunneling probabilities change gradually rather than suddenly. As a barrier grows thicker or higher, tunneling becomes less likely, but it never fully disappears. There is no point at which the universe says, never. There is only, almost never. This distinction may seem minor, but it carries enormous philosophical weight. It means the universe is probabilistic at its core, not deterministic. The existence of tunneling reshapes our understanding of causality. Outcomes are not dictated solely by energy and force. They are influenced by probability and possibility. A particle does not decide whether to tunnel. The universe samples outcomes according to mathematical rules, and occasionally, the improbable becomes real. Over vast numbers of particles and long spans of time, these rare events become inevitable. Walls, in this light, are statistical constructs. They stop most things most of the time, which is enough to define our experience. But they do not stop everything always. Their authority is practical, not absolute. They are reliable at human scales because probabilities align overwhelmingly in favor of blockage. At microscopic scales, where fewer particles and shorter distances dominate, the cracks in certainty appear. This perspective also dissolves the illusion of solidity. Matter is not made of tiny bricks stacked together. It is made of fields and probabilities arranged in stable patterns. A wall feels solid because the probabilities of penetration are vanishingly small for macroscopic objects. Not because penetration is forbidden, but because it is astronomically unlikely. The laws that allow tunneling at small scales do not vanish at large scales, they are merely buried under overwhelming numbers. Quantum tunneling ultimately reveals a universe that values possibility over prohibition. Barriers are not commands, they are suggestions enforced by likelihood. Light usually obeys those suggestions because it interacts too strongly to resist them. Some particles occasionally ignore them because the universe allows chance to speak. This hidden behavior does more than explain particles passing through walls. It exposes the architecture of reality itself. A universe built on probability is not chaotic, it is structured in a deeper way. Order emerges not from rigid rules, but from statistical dominance. Stability is achieved not by forbidding alternatives, but by making them rare. In this framework, tunneling is not a strange exception. It is a reminder that the universe is continuous, flexible, and subtle. What we call impossible is often just extremely unlikely. What we call solid is often just statistically reliable. And what we call a wall is, at its deepest level, a negotiable boundary written in the language of probability rather than certainty. At the deepest level of reality, certainty is an illusion. What we experience as solid, predictable behavior emerges only when countless microscopic events average out into stability. Beneath that surface, nature operates according to probability, uncertainty, and limits that no amount of technological precision can eliminate. This is not because the universe is incomplete or poorly designed, but because uncertainty is a fundamental feature of how reality exists. Understanding why particles can sometimes pass through walls while light cannot requires accepting this probabilistic foundation. In classical thinking, uncertainty is a weakness of knowledge. If we knew all forces, positions, and speeds exactly, we could predict everything perfectly. Quantum physics shattered this idea. It revealed that uncertainty is not about ignorance, it is about structure. Certain pairs of properties, such as position and momentum, cannot both be precisely defined at the same time. The more accurately one is known, the less defined the other becomes. This is not a technological problem. It is a rule of the universe. Because of this uncertainty, particles do not have sharply defined trajectories. They are not moving points tracing exact paths through space. Instead, they exist as distributions of possibility. Their presence is spread out, their behavior described by likelihoods rather than certainties. When a particle approaches a wall, there is no exact point where it must stop. There is only a region where the probability of finding it decreases. The wall does not say no, in an absolute sense, it says unlikely. This probabilistic structure allows outcomes that classical logic would forbid. A particle may lack the energy needed to cross a barrier according to classical rules, yet still appear on the other side. This happens because energy itself is subject to uncertainty over short timescales. The universe permits brief fluctuations that allow temporary violations of classical expectations, as long as they obey deeper conservation principles overall. These fluctuations are not errors. They are permitted behaviors within the limits nature sets. Light, however, usually does not benefit from this freedom in everyday situations. Its interaction with matter forces rapid resolution of uncertainty. The moment light encounters a wall, its electromagnetic nature triggers countless interactions that collapse probabilities almost instantly. The wall measures the light, absorbs it, reflects it, or converts it into heat. There is no extended ambiguity, no lingering uncertainty that allows improbable outcomes to grow into reality. Particles that interact weakly are not measured so aggressively. Their uncertainty persists longer. Their probability waves are allowed to explore forbidden regions without immediate collapse. This difference is crucial. In quantum reality, what is not measured is not constrained. The longer uncertainty survives, the more room there is for unexpected outcomes. Probability in quantum physics is not randomness without rules. It follows precise mathematical structures. Outcomes may be unpredictable individually, but they are statistically consistent. If an experiment is repeated many times, probabilities reveal stable patterns. This is why quantum tunneling can be relied upon in technology, even though any single tunneling event is unpredictable. Nature trades certainty of individual events for reliability of averages. Walls, from this perspective, are not absolute barriers but probability filters. They reduce the likelihood of certain outcomes without eliminating them completely. The thickness, composition, and structure of the wall shape the probability landscape. A thicker wall lowers the chance of passage, but never drives it exactly to zero. Classical thinking demands certainty. Quantum reality allows only limits. This uncertainty is deeply uncomfortable for human intuition. Our minds are built to expect definite outcomes. Either something passes or it does not. Either a door is open or closed. Quantum physics replaces these binaries with gradients of possibility. Something can be mostly stopped, almost blocked, but never entirely forbidden unless a fundamental symmetry demands it. What makes this even more profound is that uncertainty applies everywhere, not just at walls. Space itself is subject to fluctuations. Energy, time, and even vacuum are restless. Empty space is not empty. It seethes with temporary events that appear and disappear, influencing how particles move and interact. A wall exists within this restless background, not outside it. This reveals a universe that is not rigidly mechanical but dynamically flexible. Laws do not dictate exact outcomes, they define allowed ranges. The future is not written in sharp lines but sketched in probabilities. Walls feel solid because probabilities overwhelmingly favor stopping, not because stopping is guaranteed. In the end, the ability of particles to pass through walls, while light cannot, is not a loophole or a trick. It is a direct consequence of uncertainty being fundamental. Reality does not promise impossibility, it only promises rarity. And in a universe built on probability, rarity is never the same as never. Light appears powerful in everyday life. It illuminates cities, carries information across space, and travels at the fastest speed allowed by nature. Yet when it meets a solid wall, it usually fails completely, while some particles succeed in passing through as if the wall were barely there. This contrast feels backward at first. How can something as fast and energetic as light be stopped, while tiny particles manage to cross what seems like an impenetrable barrier? The answer lies not in strength or speed, but in the type of interaction that takes place at the most fundamental level. Light exists as an electromagnetic phenomenon. Every beam of light is a vibration of electric and magnetic fields moving together through space. Because of this, light is inseparably linked to electric charge. Wherever charged particles exist, light will interact with them. A solid wall is filled with charged particles, especially electrons bound within atoms. These electrons are highly responsive to electromagnetic fields. When light reaches the surface of a wall, It immediately triggers a collective reaction among these electrons. They begin to oscillate, absorb energy, and re-emit it in altered forms. This response happens so efficiently that light rarely penetrates deeper than a tiny distance into the material. This efficiency is the key reason light usually fails. The wall does not need to be thick or dense in a mechanical sense. It only needs to contain a large number of charges that can respond together. Even a thin layer of material can stop visible light because the electromagnetic interaction is so strong and so coordinated. The wall acts like a synchronized defense system, engaging the incoming light almost instantly and leaving no room for escape. Particles that succeed where light fails often do so because they are not forced into this kind of interaction. Some particles carry no electric charge, and others interact with matter through forces that are far weaker than electromagnetism. For these particles, the wall's electrons are ineffective. The wall cannot easily absorb them, reflect them, or even notice them. As a result, these particles pass through without triggering the collective response that stops light. Even charged particles can sometimes succeed where light fails, and this is where quantum behavior becomes crucial. Unlike light, which is almost immediately measured by the wall through electromagnetic interaction, matter particles can avoid direct interaction under certain conditions. At small scales, interactions are not guaranteed, they are probabilistic. A particle approaching a wall does not always collide with an atom. There is a chance, sometimes small but real, that it will pass through regions of space where no strong interaction occurs. Light does not enjoy this same freedom in ordinary materials because its very nature forces interaction. The electromagnetic wave cannot pass through a sea of charged particles without disturbing them. This disturbance effectively collapses the wave at the surface. The wall becomes a place where light's journey ends, not because of a physical block, but because of unavoidable engagement. Another important factor is energy matching. Atoms absorb light most effectively when the light's energy matches specific transitions within the atom. In opaque materials, these matches are abundant. The wall is tuned, in a sense, to absorb visible light. Matter particles do not face such a universal matching condition. Their interactions depend on much rarer alignments of energy, position, and force. If those alignments do not occur, the particle continues on its path. This difference explains why transparency exists at all. Materials like glass allow visible light to pass through, because their electrons do not easily absorb visible wavelengths. Change the wavelength, and the same glass may become opaque. Light's success or failure depends entirely on how well it couples to the material. For many walls, that coupling is extremely strong, leading to failure. For some particles, coupling is weak or non-existent, leading to success. What feels like a contradiction is actually a reflection of specialization. Light is exquisitely sensitive to electromagnetic environments. This sensitivity makes it useful for vision, communication, and energy transfer, but it also makes it vulnerable to barriers filled with charge. Particles that ignore or barely respond to these environments gain the ability to cross boundaries that light cannot. In this way, light's failure is not a weakness but a consequence of its role in the universe. It is designed, by its very nature, to interact, to exchange energy, to reveal structure. Particles that succeed where light fails do so by remaining silent, unnoticed, and unengaged. The wall stops what it can interact with and lets pass what it cannot. This simple principle explains why light so often comes to an end at solid surfaces, while some particles continue onward, quietly passing through what we once believed to be absolute barriers. Real-world evidence of particles passing through solid matter is not a theoretical curiosity or a mathematical trick. It is one of the most well-documented and experimentally verified aspects of modern physics. What makes it remarkable is that these effects are not confined to exotic laboratories or distant cosmic events. They occur constantly around us, even though we remain unaware of them. The solidity of the world is an illusion created by dominant interactions, while beneath that illusion, Particles move through matter in ways that challenge everything we intuitively believe about walls and barriers. One of the most striking examples comes from neutrinos. These particles are produced in enormous numbers inside the Sun, in nuclear reactors, and during violent cosmic events such as supernovae. Every second, trillions of neutrinos generated in the core of the Sun pass directly through Earth. They cross oceans, mountains, concrete walls, and even the entire planet without slowing down. This is not speculation. It has been measured by detectors buried deep underground, shielded by kilometers of rock. These detectors occasionally register a neutrino interaction, confirming that the particle has traveled through vast amounts of solid matter to reach them. The overwhelming majority pass through without any interaction at all. The reason neutrinos do this lies in how weakly they interact with matter. A wall stops light because light interacts strongly with electrons. A wall stops people because electromagnetic forces repel the atoms in our bodies. Neutrinos, however, barely interact with either electromagnetic forces or the strong nuclear force. For them, atoms are mostly empty space, and the probability of a direct collision is vanishingly small. The wall is not violated, it simply lacks the ability to stop them. Another powerful example comes from muons, particles created when cosmic rays strike Earth's atmosphere. Muons rain down continuously from the sky, penetrating buildings, mountains, and even underground tunnels. Experiments have used muons to image the internal structure of pyramids and volcanoes, a technique known as muon tomography. The fact that muons can pass through hundreds of meters of solid rock while light cannot pass through a thin wall of concrete highlights how misleading everyday intuition can be. Again, the explanation is interaction strength, not size or speed. Quantum tunneling provides a more subtle but equally real demonstration. In this case, particles do not ignore matter entirely. Instead, they exploit the probabilistic nature of quantum mechanics. Electrons routinely tunnel through barriers inside electronic components. In fact, modern technologies such as flash memory, tunnel diodes, and scanning tunneling microscopes rely directly on this effect. A scanning tunneling microscope can detect individual atoms by measuring electrons tunneling through a tiny gap that classical physics says they should never cross. This is not an approximation or a rare anomaly. It is a controlled, repeatable process used daily in laboratories around the world. Nuclear physics offers another dramatic example. Inside stars, including the Sun, nuclear fusion occurs because particles tunnel through energy barriers created by electrical repulsion. Classically, the temperatures in the Sun's core are not high enough for protons to overcome this barrier. Quantum tunneling allows them to pass through it anyway, enabling fusion and powering the Sun. Without this effect, stars would not shine, and life as we know it would not exist. The universe itself depends on particles passing through what should be impenetrable barriers. Even in medical science, particle penetration is used in practical ways. Certain forms of radiation therapy rely on particles that can pass through tissue to target tumors. Neutrons and other particles are used in imaging and treatment because of their ability to penetrate matter differently than light or X-rays. These techniques are built on precise measurements of how particles interact with solid material, confirming again and again that walls and bodies are not absolute obstacles. What all these examples have in common is that they reveal solidity as a selective property. Matter does not block everything equally. It blocks what it can strongly interact with and allows passage to what it cannot. This principle applies universally, from subatomic particles to cosmic phenomena. The wall remains solid to us because we are made of particles that interact strongly with it. To other particles, the same wall is nearly transparent. The existence of these effects does not weaken physics, it strengthens it. The predictions of quantum mechanics and particle physics match experimental results with extraordinary accuracy. The fact that particles pass through solid matter is not a loophole or exception. It is a direct consequence of the laws that govern interaction, probability, and scale. Real-world evidence forces us to accept a humbling conclusion. The boundaries we trust are not fundamental features of reality. They are emergent consequences of how certain forces dominate our everyday experience. Beneath that experience lies a universe that is far more open, permeable, and dynamic than it appears. Particles crossing walls is not a violation of nature's rules. It is one of the clearest demonstrations of how those rules truly work. The idea of probability and uncertainty sits at the core of why particles can behave in ways that appear impossible to the classical mind. In everyday life, we assume that objects have definite positions and definite outcomes. A ball is either on one side of a wall or the other. It either passes through a doorway or it does not. This certainty feels fundamental, but at the quantum level it dissolves completely. Nature does not commit to a single outcome until the last possible moment. Instead, it operates through probabilities, allowing multiple futures to coexist before one is realized. This uncertainty is not caused by ignorance or poor measurement. It is not that we lack better instruments. The uncertainty is built into the fabric of reality itself. A particle cannot have both a perfectly defined position and a perfectly defined momentum at the same time. The more precisely one is known, the less precise the other becomes. As a result, a particle approaching a wall is never in a single, exact location with a single, exact trajectory. It exists as a range of possibilities, some of which extend beyond the barrier. This probabilistic nature weakens the authority of classical boundaries. A wall becomes less like a solid line and more like a region where probabilities shift. The particle's likelihood of being found decreases inside the wall, but it does not drop instantly to zero. As long as the probability remains non-zero, the universe allows the possibility of passage. When a particle is detected on the other side, it is not breaking a rule. It is fulfilling one of the allowed outcomes. Light, in contrast, is typically forced into certainty much more quickly. Its interaction with matter is so strong that probabilities collapse almost immediately. The wall acts as a measuring device, forcing a definite outcome. Reflection, absorption, or scattering occurs, leaving no room for ambiguity. The difference is not philosophical, it is mathematical and physical. Probability survives longer for some entities than for others. This reveals a profound limitation of classical intuition. Human intuition evolved in a world where probabilities average out into certainty. At large scales, uncertainty becomes negligible and outcomes appear fixed. But at the quantum scale, uncertainty is dominant. Walls no longer decide outcomes absolutely, they merely influence the odds. What feels impossible is often just improbable. And in a universe governed by probability, improbable events are not forbidden. Why light usually fails where some particles succeed is not a mystery of weakness or strength, but a story of interaction. Light is extraordinarily powerful. In one sense, it travels at the ultimate speed limit of the universe and carries energy across vast distances. Yet this very nature makes it vulnerable to matter. Light cannot help but interact. It announces its presence loudly wherever charged particles exist. A wall is rich with charged particles. Electrons are bound within atoms, vibrating and responding to electric and magnetic fields. When light arrives, these electrons respond immediately. They absorb energy, shift positions, and re-radiate that energy in new directions. This response happens collectively, involving enormous numbers of particles at once. The result is a powerful, unified resistance that halts the progress of light almost instantly. Some particles do not trigger this collective response. They may lack electric charge or interact only through forces that matter barely notices. For them, the wall is not an active opponent. It does not rise up as a coordinated system. Instead, it remains largely indifferent. Without interaction, there is nothing to stop motion. Even photons, under special conditions, can display limited forms of tunneling. But these situations require carefully engineered environments where interactions are suppressed or controlled. In everyday materials, the electromagnetic grip of matter is too strong. Light is caught immediately. This contrast highlights an ironic truth. Light fails not because it is fragile, but because it is deeply connected to matter. It cannot pass unnoticed. Some particles succeed precisely because they are almost invisible to the forces that define solidity. The wall does not defeat light through strength, it defeats light through intimacy. Real-world evidence of particles passing through solid matter is not confined to theory or imagination. It is observed constantly, silently, and on a massive scale. Neutrinos stream through Earth in unimaginable numbers, produced by the Sun, distant stars, and violent cosmic events. They pass through oceans, mountains, and walls without disturbance. Entire planets fail to stop them. Cosmic rays penetrate the atmosphere and generate cascades of particles that reach the surface of Earth. Muons created high in the atmosphere pass through buildings and even human bodies. These are not rare anomalies. They are everyday occurrences, invisible only because our senses cannot detect them. In laboratories, electrons tunnel through barriers in devices designed to exploit this behavior. Modern electronics, medical imaging, and scientific instruments rely on this phenomenon. Without particles passing through barriers they should not cross, much of modern technology would not exist. These observations confirm that solidity is conditional. Matter appears solid because of dominant interactions, not because it is impenetrable. When those interactions weaken or fail, walls lose their power. What this hidden ability reveals about the true structure of the universe is both humbling and transformative. The universe is not built from rigid objects separated by absolute boundaries. It is built from fields, interactions, and probabilities. What exists is not defined solely by location, but by relationship. Walls do not exist as universal obstacles. They exist as regions where certain interactions dominate. Change the interaction, and the wall changes its meaning. Reality is not a collection of sealed compartments, but a continuous fabric where different forms of existence pass through one another unnoticed. This perspective dissolves the illusion of absolute separation. Even the most solid objects are transparent to something. Even the strongest barriers are conditional. The universe is not governed by what is impossible, but by what is unlikely. In this deeper view, particles passing through walls while light cannot is not a paradox. It is a revelation. It tells us that the universe is subtle rather than rigid, relational rather than absolute, and governed by probabilities rather than certainties. What we call solid is simply what we interact with most strongly. Beyond that interaction lies a vast, permeable reality, quietly allowing passage where we least expect it.